The objective of this program is to implement Lagrange polynomial algorithm in Python. So I have opened a online Google notebook, which is from Colab. So I start programming, coding, import numpy as empty, import matplotlib.plot as plt. Activate this library, and then the coding for the rest of the things. So in interpolation problems, we require the X data, the data points. Let's take 3 data points, store them in array, numpy array for 2, 2.5, and 4. So 3 points and corresponding ordinate values we stored in numpy array. These are 0.5, 0.4, and 0.25. So this is the data. This is the data. Okay. Now, the Lagrange polynomial interpolation, we have to construct the Lagrange polynomial and multiply them with the y value. So with this data, we can construct a second degree polynomial. So there will be 3 terms. So I require a summation, define a sum 0.0, and I have to compute 3 terms. So I write for I in range 3. There are 3 points. So the index will run from 0, 1, 2, right? So like you can write here n equal to 3 and here range 1 to 3. Okay, range 1 to n, 0 to n minus 1. So in our case, it will be 0, 1, and 2. Okay, this is fine. So we require the L to be constructed, Lagrange coefficient, Lagrange polynomial, L equal to 0. So for a given value, of x, we have to construct L. If L is equal to 0, and I write here while j is not equal to I, while j is not equal to I, so compute the L as L equal L times x minus xd of I, xd of j, right? X minus xd of j divided by x minus x I minus xd of j. Well, this should also be xd of I. Okay, so this is going to be the case, right? So here x has not been defined, which is something where that should come from our input. And also we are writing it in the product. So L should not be initialized as 1. It should not be initialized as 0. It should be as 1 because multiplicative identity is 1. So this is this. Then we have not set anything on j, right? So what should be the value of j? Right? So how to set the value of j? So I define here j equal to 0, right? And if j is not equal to I, so j, this should be computed, right? And then j is equal to j plus 1, right? And I varies from 0 to n. This is one way of the programming. Let's see whether it works or not. This is the end of J loop, and this is then when the term L is constructed, we have to update the sum. Sum is equal to sum plus L times y yd of I. So Li has been constructed from here, right? And yd is taken from the data. So this is it. This will return the value, right? So it is good to write all this one in the form of a function, since we have to provide the value of this x, right? So let's define the function. Define function Lagrange. It will take on the value of xd, yd, and an input value of x, right? And we can define n directly. We said that there are 3 points, so I can take it from the data as numpy size of xd or yd. So it will directly calculate the value of n. That will be the generalized thing. Size of vector or the number of data points. Number of data points. So we require a tab to all the things in the context of this function. Okay. And then finally the function, the Lagrange function, should return the value of sum, right? The value of ordinate. And that's it. So we have written the function, right? And now I pick up this function and put it in another cell. Right. Let's see whether the function is correct or not. This is the function generalized. It will take on the data values xd and yd. Then it requires the value of x at which the required ordinate value is required, right? We want to calculate value of y at this x, and the polynomial is going to be constructed from this calculation. So let's see whether it is free from errors or not. This is the most critical stage in my experiment. I am on virtual pendulum of excitement. If the program fails, I fell from the pendulum. Oh, it's red one. I fell from the pendulum. So there is problem in the while loop. Maybe this is not the correct way to say unequal. So let me try this one. And well, before that, you should read out the error. Okay, unmatched parenthesis. Oh, it is not the this is correct one, right? So well, I have been saved from adding another error to my program. So this was additional. Okay. Now let's see whether we got a bright right. Oh, we got a bright right. So for cleaning your clothes, you should use bright. Bright will do the right. So now data and the values. So this is the data. Now it is known to our program. Now let's use the function to get the values. Our range, our domain is 2 to 4. So within this one, where are our values? So we can use the function now, Lagrange xd, yd, and x value should be given. Let's see whether it picks up a numerical value or not. 2 to 4, I can use in between value of x to get the value of y. So 1.825, is it reasonable? You have to test yd values. We have yd values 0.5, 0.4 and 0.25. So at 3.5, at 4 its value is 0.25. So it's questionable. It's questionable. Let's plot the data and further explore. So I defined a range of x value, x numpy linear space, say from 0 to 6, and let's take some 50 points in between. And now I construct, let's first plot it for jj in range 50. I require a y to store the values. Y numpy zeros, 50 zeros, and of type float. Y of jj is equal to Lagrange xt, yd, and x of jj. For every value of x, a value of y will be generated. And let's plot the data points. Plot plt plot xt, yd as red circles, and then I plot plt plot xy, the whole set of values computed from Lagrange interpolation is a blue line. plt x label is x, and plt y label as y. Identified my error. Okay, so I'm doubtful. Oh, this polynomial is not the correct one. It is not passing through the data points. Polynomials must pass through the data points. So we have to see something. We have to correct something in our algorithm. And this is the most critical type of error. When you get the answers from the computer and you find somewhere, somehow, that they are not correct. The polynomials computed from the data points must pass through the data points. So I have to consider the structure from here. Use the other structure I use for j in in range uh, right, and I say if j is equal to I, j is equal to I, then yes, continue, then L is equal to L, and else do this calculation, right? So our only condition is that while computing the product in this one, that I and j must not be equal. Otherwise, it will be infinite, right? So let's see whether there is, the function is correct. Okay, it's correct. By Python, there are no syntax mistakes. Now let's do the calculation. So it is 0.275, a bit satisfying. It is satisfying. Now yd values, okay, this belongs to this value. So it is smaller than this value and it is higher than this value. It is in between, right? And now let's construct the polynomial whole interpolated values again. Behold, and capture this historical moment. Oh, it's great. Just like the beads. That's nice. That's very nice. So Lagrange polynomials prevail. And now if I add some more data to this one, the same algorithm is going to construct a high degree polynomial. Let's see. Why not? Let's do it after that. After that. So again, the power of algorithm. A new data set with xs is equal to numpy array. So let's take some data values 1, 2, 3, 5, 7, and of the type float. Now just for the quick estimation, I compute numpy array for natural log of xs, right? This is the data set. Given data, it may come from any experiment. And now let's do the, well, for the same range, x values, x is there and y is there. So I can write for I in range. I have got the x values, 50 values. Let me see whether we can directly compute for x vector or not. So I say xs is the data set, ys is the data set, and x is the same, right? But I'm not sure whether it is going to work or not. Let's test it. Whether the function works with the x as an array or it identify it as a number. If it identify it as a number, then I had to do the programming in the loop with the for loop. So it has identified it. Very nice. Can I see values? Let's see that all in the plot. In the plot. PLT plot XS, YS as red circles. PLT plot XY, new values of Y computed just now. And to make it a bit different, I set it with the green color. Labels are X label is X and PLT Y label is Y. Hold your breath. And myself too. Okay. So we have a higher degree polynomial. I started with the 5 points. 1, 2, 3, 4, 5. 5 points. So it is basically a 4-degree polynomial that has passed through these points, right? Since the last point was not in my domain, x, therefore it has not joined this point. So polynomial of second degree computed by the same function. Polynomial of 4th degree computed by the same algorithm. And you see, the algorithm is this one. It takes on the data values. It computes the number of data points, right? And then we have the outer loop for the summation of Lagrange polynomials and corresponding value of y. This is the outer loop structure. And in the inner loop, we have the product of x deviations, like x minus xj, deviation of x about all the points, and then the deviation of ith point about the rest of the points. So that's the structure, intelligent structure discovered by Lagrange. and then it returns the value of summation, which is the ordinate value. Amazing. Let's stop at this point.